second lesson of this subject, introducing linear algebra. And in this video, we are going to look into what are the vectors in 3 dimensions, how do they look like, a kind of a visualization. We're also going into deep into the concepts of matrix, what are the different type of matrices which are there, what are the matrix operations, and certain other things which are related to matrix and matrix algebra. Remember that this is the second lesson in the series of linear algebra. I would request those who are watching it for the first time, please go ahead and check my first video on the playlist of linear algebra, because that was the video when we introduced the concept of linear algebra, why we would use linear algebra, and certain important concepts of vectors and others. So those who have not watched it, please go ahead and watch it. However, this is the second lesson on linear algebra, and we are going to look into matrices and different other areas. My name is Shaunak and you're watching this video on my channel Physics for Students. A warm welcome to the second lesson on introducing linear algebra. So first let us see what are the topics that we are covering today. We will look into vectors in 3 dimensions. We will understand what is a matrix. We are also going to look into some of the fundamental concepts of matrices, what is called the element of matrix, different types of matrix, what is the definition of a tuple, how do we sum up the matrices, and an important theorem that is very fundamental in linear algebra. So first we will look into vectors in 3 dimensions. Now first let us visualize something like this, right? So we got a v plus w, and you can understand that v is going in this direction and w is going in this direction. And if we take the values as 4 and 2 and w equals to minus 1 and 2, then we can just sum it up as this and gives result to 3, 4. And now let us see that we see a different kind of a dimension. So first we will look into 2 dimension. So you see here what is happening. We take w equals to minus 1, 2 and v equals to 4 and 2. And here you can see that w is going down towards the, it's going below. So when we take v minus w, it gives a result as 5, 0. So what we understand quickly from is that the vector addition of v plus w, which gives 3 and 4, produces the diagonal of a parallelogram, and the linear combination on the right hand side v minus w gives v equals to 0. Now you can understand from this diagram that we travel along v and then along w, or we take the diagonal shortcut along v plus w. We could also get along w and then go into v. So whatever it happens, either it is w plus v, it is the same as it gives the answer v plus w. Okay, so now you see a vector with 2 components corresponds to basically what we call an xy plane. And the components of v are, so this is 1, the components of v are the coordinates x equal to v1 and y is equal to v2. And the arrow ends at the point v1 and v2 when it starts from the origin 0 and 0. So now we see a new set of vectors, right? v1, v2 and v3. And remember that this xy plane will be repressed by a 3-dimensional plane space, I would say, which somehow looks like this. And here are some typical vectors which have called 3 components, this one and this one, and when we add up we get something like this. So the vector v corresponds to an arrow in 3-dimensional space. Usually the arrow starts at the origin where the xyz axis meets at the coordinates 0 and 0 and 0, because it is 3-dimensional. So the arrow ends at the point with coordinates v1, v2 and v3. This is a perfect match between the column vector and the arrow from the origin and the point where the arrow ends. Okay, so now you see that we have written something. So here it is 3, 2 and we get 3 and 2. Now you see this is a 3-dimensional vector. Now you see we are moving from 1 dimension to 3 dimension. So 0 to 1 and 2 to 0. And even we want to write 1, 1, so this is something different, right? So this is 3, 2 and this is 0 to 1. This is just to show you that how we move from 2 dimension to 3 dimension. Now if you take a kind of a vector, something like 1, 1 and minus 1, we can write it something like this, right? v equals to 1, 1, minus 1. It is called a row vector, right? So what we get from here is that vectors of xy component, which you can see here, and xyz component actually corresponds to point xy, that is in 2 dimension, as well as it corresponds to xyz, which is in 3 dimension. Now we will soon see that why this 111 is written in parentheses. Let us turn the page and we see next. So this one is written something as this. Basically we call it as a row vector. It is actually a column vector just temporarily lying down, and it is written in order to save the space, because this way, if it is written in this way, it is in order to save the space. So it is actually it is a column vector just temporarily lying down. So the row vector, we can say 1 1 comma minus 1, whence it is written in this way, is absolutely different. Even though it has the same 3 components, the row vector is the transpose. Yeah, it has absolutely same 3 components. The row vector is called the transpose of the column vector v. We can add up v plus w. It has still found a component at a time, that is v1 plus w1, v2 plus w2, and v3 plus w3. These are the components of the sum. Okay, so now we understood what are vectors. From 2 dimension we move to 3 dimension. We write it in a row vector from the column, because we know in order to save them. Now what we will do, we would like to look into some of the areas or some of the concepts in which we represent data. And let us do a quick review. So we see that a vector v is in 2-dimensional space v1 and v2, and v plus w can be v1 plus w1, v2 plus w2, and if we put a kind of a constant cv, it will be cv1 and cv2 are found a component time. A linear combination of 3 vectors u, v, w is cu plus dv plus ew. I've written it in bold just to mention that these are vectors. We take all the linear combinations of either u or u comma v or u comma v in 3 dimensions. It actually are the combinations to fill up either a line or a plane and the whole space in 3 dimensions, which is R3. Now, given all these factors, we will now look into matrices. But before that, I would like to tell you why we form the matrices, what are the basic concepts of matrices, and how matrices actually helps us to solve problems, not only in physics and mathematics, but also in terms of common life or in industry applications. Okay. Now here I would like to tell you before we go ahead, in some of the books that you will see that these books first teach you linear equations and then they go to matrices. And there are some books which teaches matrices first and then they go to linear equations. We will take the second approach because there is a reason I will tell you. Matrices helps us in a better visualization of areas where linear equations, I would say these are more mathematical. These are a little bit, I would say, abstract in nature. So if you learn the linear equation first and then go to matrices, it becomes difficult sometimes for the students to understand, because from abstract concept we are going into visualization. So we will start first with visualization and then go to the abstract concept. Okay. So what does this figure actually denotes? So you see, we live in a complex world which is full of finite resources, competing demands and information streams that requires to be analyzed before resources and can be allocated fairly to the demand for those resources. Any mechanism that makes the processing of the information more manageable and visible is a mechanism which needs to be valued. I would consider a t-shirt kind of a factory, or you can say the t-shirt inventory for an average department large store. Now the t-shirt comes in different sizes and 5 colors every day, and the department supervisor prepares an inventory report for management. So you see this kind of a report: 9 T small and 5 teal medium, 8 plum small and 6 plum medium. Large sizes are nearly depleted. These are reports which are very difficult to analyze. You see that we are coming to matrices, but before that I'm trying to explain you that what is the reason and how it helps. Rather, this collection of t-shirts, if you put it in this way, it is much easier and familiar for us to understand. So we put the colors 031, teal 950, and then we put the kind of a small, medium, and large. So representing the t-shirts in this fashion becomes easier. So you can read the entire paragraph to determine the number of sand-colored small t-shirts in current stock. Here, in a rectangular array of data represented, you will find it easier to find out the t-shirts along with their sizes. Okay, given this kinds of a concept, this is what we want to represent, and I will now define what is a matrix. So we can say a matrix is a rectangular array of elements arranged in horizontal rows and vertical rows, and the array of elements sometimes looks like this. It has got 3 columns. So now we try to define them. So matrix in here has 3 rows and 2 columns, right? And it is said to have order or size 3 times 2. So it is called, it is said to have order 3 by 2, right? It's called 3 by 2. And by convention, the row index is always given before the column index. Now, if you get this kind of a matrix, it has order 3 and 3, 3 times 3, and it is called as 3 by 3 matrix. And then we get this one, which has order of stock matrix, something like this, and we call it 3 by 1. And this is called, it is said to be 3 by 1. Okay, so what we get from here is that the entries of elements, that is whatever is mentioned inside, it can be numbers, it can be anything. These are called elements, and we use uppercase boldface letters to denote matrices and lowercase letters for elements. So the letter identifier for an element is generally the same letter as is the host matrix. Now you see 2 subscripts are attached to elements which are able to undefine the location in a matrix. The first subscript specifies the row position, and the second subscript denotes the column position. So let us see an example. Here is the matrix, and if you use L12, for example, in order to denote the matrix L, then it is the meaning that the element in the first row and second column, which is 3. You can understand the first row and the second column. Now, if I take this one and denote it as M32, then it means element in the third row and the second column, and it shows M32 equals to 4. Okay, now that we have understood the matrix and how we represent, I would like to, show you what the different types of matrices which are being formed. Okay, so in general, and in general, a matrix, say for example A of order P, I would say P times N, something looks like this. And it is generally written as with a small number, say A sub Aij. I mean to say it is written with a kind of a subscript Aij and P times N, and it can also be written just as Aij. Why? Because P times N, order of Pn is quite common, right? So that is how we write it. Now this denotes the element of the ith row, and J denotes of the jth column. Now, and any element having its row index equal to the common column index is a diagonal element. So for example, this one, this is the diagonal 1 and 2. Here this is 4, 2 and 2. And because it is 1, it has got 19.5. That is the only one, right? So this is what is called a matrix of order, and this is written with the row index and column index is called the diagonal element, and Aij means the ith row and jth column. You can just skip P times N and write it as Aij. Now, I would like to take a pause here. The reason is that you see these matrices and the way we are learning this indices, the subscript, etc. These will come to a lot of use both in physics. And if you go to my playlist in mathematics for quantum mechanics, although we will start with matrices today, these will be very important. So I would request all the viewers who are watching this video not to skip this part, and it is important to learn, because be it quantum mechanics, be it stress energy momentum tensor, be it relativity, these things are going to be very important. These indices, column, and the operations that you are learning, it will be true for every part. Okay, now what is called a square matrix, for example? So a matrix is a square if it has got the same number of rows and columns. You can see this is something which is a square, and these elements A11, A22, A33 and so on up to AMN, these are called the principal or diagonal. So let us write it once again. Yes, it is. This should be NN anyway. So this is called the main or principal diagonal, right? And the elements of the matrix always are not numbers. They can be functions themselves, as we will see. For example, this matrix and this matrix and this matrix. You see there is no number. It can be exponential, it can be an integral, it can be trigonometric functions also. Just to make you aware that always the elements or the entries of the matrix are not necessarily numbers. They can be anything. Okay, so what is a row matrix? This is just definition. A row matrix is a matrix having a single row. Column matrix, a column matrix is having a single column, and components are basically the elements of such a matrix are commonly called components. Dimension, the number of components in its dimension. Now this is very important because we will see in general relativity and other areas of physics that how matrices denotes dimensions, especially in special relativity and upwards we will see 3 and 4 dimensions. So in that case matrices are also equally important. We use boldface letters to distinguish rows and matrices from general matrices. So you see x equals to 1, 2 and 3. This is a 3-dimensional column vector, and this one is basically it is a 4-dimensional row vector. You see that x and u here it is written in bold just to denote that these are actually vector components. Okay, now we come to something very important. It is called a tuple. Now the term tuple refers to either row matrix or a column matrix having dimension of n. So the term n tuple refers to either a row matrix or a column matrix of dimension n. So if we take something like x equals to 1, 2, 3, it has got a 3 tuple. This one it has got a 4 tuple, right? Now what is called an equal matrix? Now two matrices are equal if they have the same order and if their corresponding elements are equal. That means two matrices A, which is equals to A sub ij, and B, which is called B sub ij, are equal. They have the same order and if their corresponding elements are equal. I think it is quite obvious. So let us see an example. So if you see here 5x plus 2y, x minus y equals 7 and 1, it means that this equals to this and this equals to this. Okay, now that we understood matrices, let us see one simple operation, then we'll go to what is called the summation of matrices. Now we take the same t-shirt example and we take another which comes by the evening. So S is something which is coming to the inventory in the morning and D is coming to the evening. And now you see that we need to add it up. How do we do this? So S and D, we just do this, right? So here you see 0 adds to 9 and 3, then this 3 adds to 3 becomes 6 and 6 plus 1 goes to 7. Right. So this is how the addition, don't worry, we will see more complex example of additions as we proceed. So once we get this kind of a matrix, we say that the sum of two matrices of the same order is a matrix obtained by adding together corresponding elements of two matrices. For example, if we get A sub ij and B sub ij have order Pn, then we say A plus B equals to A sub ij and plus B sub ij. I have not mentioned, but you understand that I goes from 1 to 3 up to n and P goes to up and J goes to 1 to 3 up to n. And remember here, there is one important point that addition is not defined for matrices of different orders. This is very important. That means you cannot add up matrices which has got different orders. Let us see a quick example of that. So here you see here we have got 3, 3, so it adds up. So this is okay. Here also you can see that these things add up. This is also okay. So we can put a green tick mark against it. Here also you will see this 2, 2, this adds up and this we put a green tick mark. But here you will see this one and this one. This is actually not allowed. So this is important that we cannot add up matrices which has got different orders and we know what is an order. So this brings back to one important theorem that if matrices A, B and C all have the same order, I mean to say three matrices have the same order, then the commutative law of addition holds, which means A plus B equals to B plus A, and B, the associative law holds, that means A plus within parenthesis B plus C equals to within parenthesis A plus B plus C. This is a kind of a theorem. I mean to say it is not a theorem, it actually comes automatically when we look into the laws of the order and addition. Question is that, can we prove this? And this is what we are exactly going to do into the next video. We are going to prove this theorem and we are going to look up further. So what are the things that we will look into the next video? Let us have a look onto that. So these are the topics that we are covering in the next video. We will first try to prove this theorem which we just saw. Then we will look into subtraction of matrices, product of matrices, what a complex matrix is, and matrix multiplication. So that's it for today's video. I think that we are going slow but steady And you know there's a proverb like slow but steady wins the race. So once we complete the matrices part, then we will go into linear equations, which is a little bit abstract, but it is very fundamental. Thank you for watching this video. Please put up your comments regarding this video on linear algebra, and please do subscribe to my channel Physics for Students. Click on the bell icon and click on all to get all the notification from Physics for Students. I'll be back with this next series and it will continue for this series in linear algebra. Till then, goodbye and do take care.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.